Okay, Organic Chemistry 2, Chemistry 3111. This is Chapter 13, which deals with ethers and epoxides, thiols, and sulfides. So we're kind of covering a total of 4 functional groups in this chapter. Ethers and epoxides are both functional groups that contain oxygens, right? You know what an ether is by now. It's an oxygen flanked by 2 R groups. An epoxide is something that we would have mentioned in Organic Chemistry 1. It's when you have a 3-membered ring with an oxygen in it. So it's like a cyclic ether in a way. A thiol is the sulfur analog of an alcohol. So you take an alcohol and you replace the oxygen with the sulfur. And then a sulfide is a sulfur analog of an ether. So when you have a sulfur flanked by 2 R groups. We're going to talk about all these functional groups. We're going to spend most of the time talking about ethers and epoxides. So let's get started. Section 13.1, what is the ether functional group? Well, I just mentioned on the first slide, but an ether group includes an oxygen atom that is bonded to 2 alkyl groups. These 2 alkyl groups, they can be the same or they can be different. So we could put R and we could put R prime on the other one like that. A trap that students fall into once in a while, not often in Organic Chemistry 2, but is that they might fall into a trap where they see a functional group like this, which is actually an ester, and they'll say, well, look, I have a carbon here and a carbon here, and I have an oxygen in between. That's an ether. Well, remember, when you're looking at functional groups, you have to always take the 30,000-foot view, right? You have to look at the entire thing before you make a judgment. And so this is an ester. It is not an ether. So don't fall into that trap. As far as those alkyl groups, or sorry, those R groups, they can be alkyl groups, right? They could be a methyl, ethyl, propyl, butyl, so on and so forth. It could be an aryl group, like an aromatic ring, and it could also be a vinyl group. All right, so it could be any one of those. It says not an acyl group, and if you're like, what's an acyl group? An acyl group is when you have a carbonyl like this, okay? Because if it was an acyl group, then you would have an ester, okay? So it can be an alkyl, aryl, or a vinyl group attached to that oxygen. Well, where do we find ethers in our everyday life? Well, ether is a common functional group in many synthetic and naturally occurring compounds as well. One that you've probably heard of is Prozac. It was a really popular drug and still remains a popular drug. I think it was first marketed by Pfizer, and anyhow, that's neither here nor there. But you can see that in the Prozac molecule, we have an ether functional group, right? We have that oxygen, we have an aryl group over here, and then we have an alkyl, and then there's some other stuff dangling off of that. What else? You can see that vitamin E is also kind of interesting. It's got an ether inside it. And then if you look at morphine, okay, if you look at the structure of morphine, which you can see is a pretty complex structure. You've got a bridge in there. You've got a bunch of rings. You've got, 5 different rings. It's a nitrogen in the bridge there. You got a couple of hydroxyl, so it's also an alcohol. But you see that there is an ether inside morphine right there. All right, so those are kind of interesting. So Prozac, morphine, what else? Vitamin E, yes. So how do we name an ether? Well, there's a couple of ways that we can name an ether. The first one that we're going to look at is what are called common names. And you can imagine that common names are common. Okay, we use them all the time in organic chemistry. Usually we use common names for smaller ethers, and I'm going to show you some examples now. So what we do is we look at the 2 R groups in the ether, and then we arrange them alphabetically, and then we slap the word ether on the end. So if you had this ether right here, well, what have we got? We've got a methyl group over here. We've got an ethyl group over here. We put them in alphabetical order. E comes before M, so we have ethyl, methyl, ether. The next one, we have a tert-butyl group here, and then we have a methyl group on the other side. Remember that the alkyl group tert-butyl is alphabetized according to the letter B. Remember that we ignore all prefixes except iso, cyclo, and neo when we're talking about alkyl groups. So we would have tert-butyl methyl ether, which is actually the correct name of this compound because we've listed the 2 alkyl groups in the correct order, right? We've put them in alphabetical order, but this compound actually has an acronym, which is MTBE. So even though the name is tert-butyl methyl ether, right, it should be TBME, but that would just be too easy. We don't call it that. We call it MTBE, which is methyl terbutyl ether, which again isn't the correct name. So the book even tells you that. It says the acronym is incorrect, or it follows the incorrect name. But the reason I'm bringing MTBE up so much, like why do you keep harping on this one ether? It's because MTBE used to be used as an additive in gasoline. It prevented knocking in a car engine. And the problem with MTBE is that it was found as a contaminant in groundwater. And I don't remember exactly where it was found first. I think maybe in the northeastern United States. And so they started phasing it out. But another note about MTBE is that it's oftentimes used as solvents or as a solvent rather, in organic chemistry. I did a lot of chemistry where I used MTBE as a solvent in organic chemistry. So those are common names. Another one that you're going to see a lot, would be something like diethyl ether, right? If you had two ethyl groups, this would be diethyl ether. But this solvent is used so much that we just shorten it to ethyl ether. So you can call it diethyl ether, or you can just call it ethyl ether. Either one is fine, okay? Widely used as a solvent. For example, all those Grignard reactions that we looked at? Yeah, we spent a lot of time talking about Victor Grignard's chemistry. Well, oftentimes diethyl ether is used as a solvent in those reactions. Now, what if you have an ether that's more complex than something simple, right? Something common. Well, for that, you have to use the IUPAC, what's called the systematic name. So common names are still accepted by the IUPAC, but a systematic name is just where we follow a set group of rules that makes it easy to name compounds that are, more complex. So here's what you do. You take the larger of the two R groups. Remember that an ether has an oxygen flanked by two R groups. So let's say you take the larger one, okay, and that's going to be your parent. And then the smaller one, that's going to be considered an alkoxy. So you take all of this together. Right now, if you're like, what the heck is an alkoxy substituent, right? If you have a methyl attached to an oxygen like this would be called a methoxy. If you have an ethyl attached to an oxygen, this would be called an ethoxy, right? And it would go propoxy, isopropoxy, tert-butoxy, butoxy, isobutoxy, so on and so forth. So that's where those come from. So here you have it. You have the alkoxy substituent attached to your parent. So if you look at this ether over here, the longest carbon chain has what? It's got 1, 2, 3, 4, 5 carbons in it. So this is some kind of pentane, and you have an ethoxy group on carbon number 1. So you would call this 1-ethoxy pentane. Okay, so again, those are the two methods that we have for naming ethers. We can either go with the common name, which again we use for ethers where they have really simple alkyl groups that you would know already. And when you have ethers that are more complex, well, for those you're going to use systematic names. With that in mind, let's take a look at a problem here. And it asks us to find or to provide an IUPAC name for each of the following. So what it's asking really is it wants a systematic name for all of them. And at the end, if we can give actually only the first one could I really give a common name to. So let's try the first one. The first one, we want to find the longest carbon chain. Well, the longest carbon chain in here has 1, 2, 3 carbons, right? There's no carbon chain longer than that. Over here, we only have 2 carbons. So if the longest chain contains 3 carbons, that means that this is some kind of propane, right? 3 carbons is propane, so this is some kind of propane. And then we have our alkoxy group over here. Well, we have an ethyl group attached to an oxygen, so that's an ethoxy. And that ethoxy group is on the second carbon. So this would be a 2-ethoxy propane. So 2-ethoxy propane, just like that. And I'll bring it together a little bit to make it a little bit neater. So that would be the systematic name. Again, just me taking a quick glance at these problems. There's really only one here that I could give a common name to, and that would be this very one. If I just redraw the compound quickly, okay, you know that this side, this is an isopropyl group here, and this is an ethyl group. So this would be ethyl isopropyl ether. So you'd call this ethyl isopropyl ether. Again, this would be the common way of doing it, but that's not what we're doing here. And again, Mr. Dion wouldn't be able to come up with good common names for these. I suppose I could if I really tried, but anyhow, let's take a look at the next two. Next one, we have another 3-carbon chain, right? If you look at this molecule, the longest carbon chain in here has 1, 2, 3 carbons in it, like that. Notice that I numbered it going from right here instead of the other option, which would have been 1, 2, 3 like this. Then I've got my ethoxy group on the 3rd carbon. I still have my chloro on the 2nd carbon. So if I switch it around, you can see that it makes much more sense because I have my ethoxy at carbon 1 and I have my chloro at carbon 2. So I've got a 1 ethoxy and a 2 chloropropane. So the 2 chloro would come first, right, based on alphabetical order. So this would be 2 chloro 1. So this is a 2 chloro. Maybe I'll spell the whole thing out here. This would be a 1 ethoxy, and it's a propane. So the only thing that's left to figure out would be the stereochemical configuration at carbon number 2. I got it figured out in my mind. Can anybody tell me, would this be R or S without looking at the solutions manual? And remember, this is a safe space. If you get the question wrong, it doesn't matter. This is just us practicing, kind of riffing in class. All right, I see a couple people are saying S. That's what I got in my brain. Let me see here. Let me check. My brain's been wrong before. If I draw this like, oops, I could draw a proton a little neater than that. There we go. The chlorine is going to be highest priority. This group will be 2nd highest. The methyl will be 3rd, and the proton is in the back. So we're going like this, which is counterclockwise. So yeah, this is definitely an S compound. So let's place all that. So if we put all that spinach together, we've got S. We've got 2 chloro, 1 ethoxy propane. Just like that. And then we have 1 left here. Well, this is some kind of benzene, right? The longest carbon chain clearly has 6 carbons in it. So this is some kind of benzene. Notice that you've got an ethoxy substituent here. You've got a chloro here and a chloro here. So how would we give everything the lowest possible number? We'd have to call this number 1, this number 2, this number 3, and this number 4. So we'd have a 2,4-dichloro. Let's write down what we know. We've got 2,4-dichloro. Nope. Dichloro. There we go. We've got a 1 ethoxy, and we've got a benzene. So we've got to put all that together somehow to make a beautiful name for this molecule. Well, the di we ignore. We got the letter C and we've got the letter E. So C comes before E. So let's put this all together. I just noticed that I made one little error here. Technically, you don't have to call this a 1-ethoxy. This can just be ethoxybenzene, because since it's the highest priority group, since it's got an oxygen in it, you don't really have to call it 1. Okay. I mean, it's not really splitting hairs. I mean, this is actually a mistake that I made there. But I wouldn't say it's the end of the world. You'll still be able to figure out the name. It's not like I'd give you an answer in a multiple choice where I have, 1 ethoxy and then no ethoxy. I can't imagine me digging in my heels that much. So you'd have 2,4-dichloro ethoxybenzene. Dichloro ethoxybenzene, just like that. There you go. So that's a little bit of ether nomenclature. Again, the reason I posted that video in my announcements today is because ether nomenclature and epoxide nomenclature, which we're going to look at later on, is not simple. Okay, if it was simple, everybody on the street would be able to do it. It is not simple. Okay, it takes a little bit of practice. So make sure you take a look at all of the practice problems that deal with nomenclature of ethers. Well, what about the structure and properties of ethers? In general chemistry and in organic chemistry 1, we spend quite a bit of time talking about valence shell, electron pair repulsion theory, or VSEPR, right? And you know that water has a bent molecular geometry. It's got a bond angle that's less than 109.5 degrees, right? Because you've got the lone pairs that push these bonds down a little bit. Well, if we look at the molecular geometry of an ether, it's very similar, right? You've got 2 R groups, okay, and you've got 2 lone pairs on that oxygen. So this bond angle is going to be close to 109.5 degrees. So we can even move this over here and we'll just say close to, somewhere near there, close to tetrahedral, or sorry, close. It's bent is the molecular geometry, but the electron geometry is close to tetrahedral. So remember that oxygen that has a steric number of 4 is sp3 hybridized, right? It's got a steric number that's equal to 4. Remember the steric number? You tally up the number of sigma bonds plus lone pairs. So you've got 2 sigma bonds and 2 lone pairs. So steric number of 4, it's sp3 hybridized. But you can imagine that the bigger that R group becomes in my ether, the more it's going to push the 2 alkyl groups or aryl groups or whatever they are. It's going to push them further and further away. And the bond angle gets bigger and bigger and bigger. Okay? As long as you know it's close to 109.5, and as long as you know that as the R groups get bigger, the bond angle will get bigger. That's really, what you need to know. What else can an ether do? Well, remember the alcohols? Remember this from the alcohols chapter? We talked about hydrogen bonding, and we kind of reviewed that a little bit. I reminded you that a hydrogen bond is nothing more than a dipole-dipole force. It's just a really strong one. Okay, that's all it is. And everybody here should be able to represent hydrogen bonding like this. This is an alcohol, and this is an alcohol. Well, an ether doesn't have an oxygen-hydrogen bond, does it? However, an ether does have an oxygen in it. And those oxygens, of course, have 2 bonds and 2 lone pairs. And so the lone pairs on the ether oxygen, we say that they're hydrogen bond acceptors. Right, if I have 2 molecules of ether, right, let's say I have an ether here, and I have another molecule of an ether like this. They cannot hydrogen bond to each other, right? There's no ability for them to hydrogen bond. Okay, there's no oxygen-hydrogen bond in what's inside this green circle. However, an ether can hydrogen bond with an alcohol or with water. It can be a hydrogen bond acceptor. It cannot be a hydrogen bond donor. And that's why ethers like diethyl ether, you can solubilize some small amounts of alcohol, some alcohols in them, not all alcohols. Now, if we were to compare the boiling points of ethanol, dimethyl ether, and propane, right, these are the kind of things that should be, and I don't mean to sound intimidating or anything, but these are the kind of trends that should be very abundantly clear in your mind as to why this is. If you look at all 3 of these compounds, they're not constitutional isomers, right? Propane doesn't have an oxygen. However, they all have similar molar masses, right? Close enough. And look at the difference in the boiling points. You go from ethanol to dimethyl ether to propane. Well, why is that? Because the alcohol, the strongest intermolecular force it can experience is hydrogen bonding. The strongest intermolecular force that the ether can experience would be the dipole force. And the strongest force or intermolecular force that propane can experience would be the London force, right? So remember that hydrogen bonding is the strongest of the intermolecular forces, and dipole intermolecular forces are stronger than London forces. However, another point I want you to follow me on here is look at this. Look at these 2, the ether and propane. They have really low boiling points, -25. That's like, getting frostbite, okay? Especially -42, okay? I mean, that's extremely cold. But look at ethanol. Look how much higher the boiling point is, 78 degrees Celsius. That'll burn you, right? If you were to stick your hand in something at 78 degrees Celsius. So what's my point? My point is just for you to really understand or to really take notice of how much stronger hydrogen bonding is than dipole forces and London forces. All right. Something else, if we compare a group of ethers, here we go from dimethyl to diethyl to dipropyl ether, right? Why are the intermolecular forces why are the boiling points increasing? Right? The only thing they experience are London forces, or an instantaneous dipole, or a fleeting dipole moment, whatever you want to call it. They all mean the same thing. But the reason why is because the larger the ether, the more London dispersion forces they're going to feel, right? Think about it. If I had another molecule of dimethyl ether next to this one, are there going to be some intermolecular forces experienced between the 2? Sure. Right, but if I have another molecule of dipropyl ether, I'm going to have a lot more intermolecular forces between it and another molecule of itself, and therefore we have increased London forces, and the temperature or the boiling point rises. I don't know if I gave you this explanation or not. I don't remember if I did this with you, so forgive me if I did this already. But if you took organic chemistry 1 with me, you might have heard me say this, okay? When it comes to London forces, and that's what's going on down here, imagine you had a piece of Velcro. Do you guys know what Velcro is? Like, do I? My sneakers are Velcro, so weed. Okay, well, if you had a piece of Velcro that was, let's say, 1 inch long, and you had to tear it apart, like, it makes that cool sound when you rip Velcro apart. I mean, would that take some of your energy? Would you be using up some of your ATP in your body to rip apart, a 1 inch long strip of Velcro? Sure. Yeah, absolutely. What if you had a piece of Velcro that was, I don't know, my piece of Velcro is, we'll say it's broken here. I'll have it like, okay, I have a piece of Velcro and it's, it's, let's say it's, I don't know, 1 mile long. Okay. It's 1 mile long. It's still the same forces that are holding the piece of Velcro together, isn't it? Still the exact same forces. But would it take more of your energy to rip it apart? Heck yeah. You'd be like, tearing it, catch your breath and keep going. So think about it. It's the same forces, but there's just a lot more of them. And the more of them there is, the more energy it takes to separate those molecules from the liquid phase and put them into the gas phase. Kind of neat. Anyhow, let's take a look at some structures and properties of ethers. Some ethers that are used as solvents. Ethers are used as solvents a lot in organic chemistry. Why would that be? The reason is ethers aren't that reactive. Okay, if you think about everything that we look at, at least 80% of what we talk about in organic chemistry too is just reactions. Yay! It's like reactions all day and all night. Well, I'm here to tell you, my friends, that ethers, are there reactions you can do with an ether? Sure, and we're going to look at some. Are there reactions you can use to make ethers? Yeah, definitely more. But what I'm saying is that when you have an ether, there's not a lot you can do with it, okay? But we can take advantage of that because the fact that ethers are relatively unreactive, they're going to make really nice solvents for reactions, okay? So diethyl ether, like we saw, is a liquid at room temperature. It's got a boiling point of what, around 35 degrees Celsius is what we said. So it's got a pretty low boiling point. But furan has an acronym, which is THF. I promise you, and I don't promise things to people very often, but if you go into the organic chemistry literature, let's say you went over to the Kramer Family Library and you opened up some, journals that deal with organic chemistry, like maybe JOC, the Journal of Organic Chemistry, and you were to look at reactions that are done in there, you're going to see THF come up all the time. Why? Because it's such a great solvent in organic chemistry. It's really stable and it's low boiling enough that it's easily removed by evaporation. This might be something that isn't really a consideration for you in chemistry 3111. You're like, I don't care if you're going to burn it. Okay, but I want to tell you right now, my friend, if you're in the lab and you're doing a reaction in a solvent, you want to make sure that it's a solvent that you can remove. Okay, if you can't remove it, then you're up the creek. Another one that's commonly used is 1,4-dioxane. Dioxane is oftentimes used for lyophilization. I don't know has anybody here ever had astronaut ice cream before? You guys know what that is? You can buy it at like novelty shops sometimes. If you're wondering, Mr. Dion, what does astronaut ice cream have to do with organic chemistry? Well, if you've ever had astronaut ice cream and it doesn't look like anybody ever has, I recommend it then. I recommend maybe you could buy some from Jeff Bezos or something and have it delivered to your house by tomorrow. But lyophilization is the process of freeze drying. Okay, and dioxane is a solvent that is often used to freeze dry organic molecules. So I won't say any more about that. All right, there we go. So the whole section about crown ethers is a section that we skip. Again, whenever I skip a section in Organic Chemistry 1 or Organic Chemistry 2, it's because it's content that's covered in our textbook, but it's not going to be covered on an ACS final. Probably won't show up on something like an MCAT or a PCAT or something like that. However, if you have an inquiring mind, I would recommend reading it. It will not take long. I promise you, it will take you, 5 minutes at the most, okay? You'll learn about 18 crown 6, 15 crown 5, 12 crown 4. So it doesn't take very long to do that. And basically it explains how crown ethers can be used to solubilize metal cations and what that's used for. All right, so let's get into section 13.5, which deals with making an ether, right? That's my way of saying the preparation of ethers. How do you make an ether? Um, Diethyl ether, which I hate it when my slides do this. You can see it's over here on the far right. Diethyl ether, again, is often used as a solvent in organic chemistry. So here in America, we need to produce a lot of diethyl ether, right? To do a lot of different reactions and reactions on large scale. And how do they make it? They actually start with ethanol. Okay, so just ethyl alcohol. And if you're like, well, where do you get that from? Corn or anyhow. So they take ethanol and they literally just treat it with strong acid is all they do. So they take ethanol, they treat it with a strong acid, so that's hydronium represented here. You convert the hydroxyl into a good leaving group, and then another molecule of alcohol is going to come in here, do an SN2. You do another proton transfer, and there you go. You end up with diethyl ether. So we abbreviate it like this, ethyl, and then we put two of those, and then an oxygen. So that's an abbreviation of diethyl ether. This is a mechanism I want you to know. Okay, I didn't put this up here just for fun. You must know this mechanism. However, there's something interesting about this mechanism and this way of making an ether is that really the only time you would use this, or the only time I can think of that I would ever use this, is if I wanted to make a symmetrical ether. Okay? When my two R groups are identical, right? When those two R groups are the exact same, you can use this method. And it works really well. It's a great way to make an ether. Anyhow, again, I don't know if I've ever actually done this reaction, and I've done a lot of reactions in my time, but I've done reactions, I would say, similar to it. Now, if you're wondering, okay, well, if I can only use this reaction to make symmetrical ethers, okay, that's cool, and you told me I have to know it. Yeah, you do. What if I want to make an ether that's unsymmetrical, right? Like, what if you wanted to make an ether where you have a methyl group on one side and an ethyl group on the other? You can't make it this way. Okay, how would you do it then? Well, you would use a synthesis that's named after a person. Okay, so this is a name reaction, Williamson. It's actually named after a scientist named Williamson. So we call this the Williamson ether synthesis, a very important reaction. I don't know if you guys are doing this, if any of you are taking Organic Chemistry 2 lab right now with Mr. Geiger. I don't know if you're doing this in the electronic lab, but when the labs are face-to-face, we always get our students to do a reaction wherein they do a Williamson ether synthesis. Such an important reaction. It's not a new reaction, but it is a very important reaction, and it's still widely used to this day. Why? Because we haven't found anything better. It's such a good and powerful reaction. So here's what you do if you want to make an ether using the Williamson ether synthesis. You start with an alcohol. You see that you've got an oxygen that's attached to one R group, so you've got to figure out what the other R group is, and here's what you do. In the first step, you treat it with sodium hydride. So remember, this is called sodium hydride. And you should all know what a hydride is. A hydride, right, is H with two unpaired, a lone pair and having a negative charge. So this can act as a good base. So here's my hydride. It abstracts the proton from the alcohol. So not only do you make the alkoxide, but something that is not shown is you end up making hydrogen gas. That's going to go up into the atmosphere. So you want to bet your bobby socks that this is an irreversible reaction, right? So then you've got the alkoxide. This is what? This is a good nucleophile. Good nucleophile. And if you're like, well, Mr. Dion, it could also be a good base. Yeah, it can be. Absolutely. But if you react it with a primary or a methyl alkyl halide, it's going to do an SN2 reaction, isn't it? All right? And now look what you've got in the end. You end up with that unsymmetrical ether. Now I'm going to address this part right here, because if you're like, Mr. Dion, that's not going to work if it's secondary alkyl halide or a tertiary, then you're just going to get mostly elimination or all elimination, and you're 100% correct in assuming that. Okay, if you're like, stop, you would be 100% correct in assuming that. And if you're lost, if you're like, I'm not sure what you mean, man. Okay, I'm not sure what you mean by this. Okay, since this reaction here, the second step, is an SN2 reaction, okay, why does it only work well with primary and methyl alkyl halides? Doesn't work with a secondary or tertiary. Let me show you. Okay, let's consider two possible routes to that famous compound, terbutyl methyl ether, or MTBE, as it is incorrectly, named using acronyms. Okay, well, on one side of this ether, you've got a tert-butyl group over here. And on this side, you've got a methyl group. So hypothetically, now again, this is hypothetical, you've got two possible starting materials. You could start with this, which is tert-butanol, and you could start with this, which is methanol. Now, if you deprotonate tert-butanol, right, in the first step, okay, what do you make? You make tert-butoxide, okay? And in the second step, what's your electrophile? It's methyl iodide. So look, you have the nucleophile and you have a primary alkyl halide, or sorry, a methyl halide. So you're just going to do an SN2 like that, and it's going to work no problem. So therefore, if we were using the Drake meme, you guys know the Drake meme where he's like, you know, thumbs up or whatever. Anyhow, so this would be a perfectly legitimate way to make MTBE. Consequently, or however, if we were to start with methanol, we would do the deprotonation using sodium hydride. Let's draw what we would end up with. After the first step, you would end up with methoxide. The problem is, in the second step, you're treating it with a tertiary alkyl halide. That is not going to do an SN2, is it? That's going to do an elimination reaction, won't it? Right? Think about it. If you go back to chapter 7 in Organic Chemistry 1, you've got a strong base, strong nucleophile, and you've got a tertiary alkyl halide. All you're going to get is E2. Right? This is what's going to happen. You're going to abstract this beta proton, and boom, lose your leaving group like that. And all you would end up with, sorry, I'm having a problem with my MacBook. Just give me 2 seconds of a lamb's tail. But anyhow, I can still write here. You would end up with isobutylene. You would end up with this molecule. That is not an ether, is it? That is not an ether, okay? So that's not very helpful. Give me a thumbs up if you just follow me on the concept here. Or if you have a question, stop me. Because we're not really going to stop here at the moment. We're going to come back to this concept a little bit. But I want to talk about something else first. Okay? Look, again, for a guy who says he doesn't ever promise anything, I'm making a lot of promises today, aren't I? I promise you that this is going to show up on your quiz. Okay, I'm going to ask you some kind of question about, you know, is this an appropriate way to do a Williamson ether synthesis? Will it work with a tertiary or secondary alkyl halide, right? And the answer is no, it won't. Okay, you're mostly going to get elimination in that case. Maybe I should cross out this reaction arrow like that. Okay, there we go. So let's talk about another way. I don't know if you remember the story I told you the other day about organic chemists and how many different ways there are to do every kind of transformation in organic chemistry, right? Markovnikov addition, anti-Markovnikov, substitutions, eliminations, oxidations, right? Look at all the different oxidations. We had Des-Martin, we had Swern, we had Jones. Then reductions, we had lithium aluminum hydride, sodium borohydride. Why do we have to know so many ways to do everything? Well, I could just tell you it's just because, but that's not really the best answer, is it? The reason why is because many times, you know, some reactions that might look really good on paper might not work in the lab when you're working with a new molecule that's never been investigated before. And so a good organic chemist, she or he, should always have many different ways of doing the same type of transformation at their disposal. Well, with that in mind, let me show you another way to make an ether. I just skipped ahead here for nothing. And that is using what's called alkoxymercuration demercuration. Now, this reaction here, this is not alkoxy, this is oxymercuration demercuration. And this we looked at way back in chapter 6. When you take an alkene, and in the first step, so this is review, right? This reaction is a review. And we covered this in chapter 11, where you start with an alkene, you treat it with mercuric acetate in water, and then in the last step, you treat it with sodium borohydride. So this is oxymercuration demercuration. Now, when I showed you this in Organic Chemistry 1, and I know because I was there, I did show you the mechanism. I told you that I would never ask you direct questions about it, but I said it was a good idea to have some kind of knowledge of this mechanism. So what you really need to know is this reaction occurs with Markovnikov regioselectivity. So you end up making what's called a mercurinium ion, and then water comes in and it attacks at the most hindered carbon, or the most substituted carbon of the double bond. Now, here's the question. What if you replace the water with an alcohol, right? What if you used an alcohol as the nucleophile instead of water? Well, instead of using water and making an alcohol, you can use an alcohol and you end up with an ether, right? We have carbon, oxygen, carbon right there. So this has got a new name. It's very close to the last one. It's called alkoxy. So it's alkoxy mercuration, demercuration. And again, it's where you're using an alcohol. Here we also have Markov-Nikov regioselectivity. And if you're wondering, hey, wasn't this used to avoid carbocation rearrangements? Sure. Yeah, so you won't get any of those either. But what do you need to know as a Chemistry 3111 student? You need to know that when you take an alkene, you treat it with mercuric acetate and an alcohol. And the alcohol that you choose, how are you going to know what to choose? Because whatever you want this R group to be, that's going to be the R group of your solvent. Okay, that's your first step. And then you treat it with sodium borohydride in the second step. And there you go, my friend. Hot dog, we have a wiener. We have the Markov-Nikov addition of that alkoxy group, right? The rich are still getting richer. The side that had the more hydrogens is the one taking the hydrogen. And the other side is now, instead of becoming an alcohol, it's becoming an ether. Brand new reaction for you in Chemistry 3111. Really powerful reaction. Well, with all of that information in mind, and that's quite a bit of information about making ethers, the next question says, show reagents that you could use to prepare each of the following ethers by a Williamson ether synthesis and explain your reasoning. So you remember that the first step in the Williamson ether synthesis was to use sodium hydride, and then the second step used alkyl halide. But you want the alkyl halide to be primary or methyl, right? If you think about this ether over here, I mean, you could break it on either side. If you were to break it here, right? If you were to break that there and start with the alcohol on this side, then your alkyl halide would have to be this. Let's use an iodide just for, we got lots of money, okay, for interest's sake. And if you broke it on this side, then your alkyl halide would be this. Which one of these would be the best alkyl halide to actually use in a Williamson ether synthesis? Would it be the one in red or the one in blue? And it's not a trick question. Which one of these would be the best alkyl halide to use in a Williamson ether synthesis? Red or blue? Well, what kind of alkyl halide is the red one? This is a primary alkyl halide, right? This carbon is only attached to one carbon. This one is a secondary alkyl halide, right? This carbon is attached to two carbons. And so remember that the Williamson ether synthesis is only going to work when our electrophile is either a methyl or a primary carbocation. So we're going to want to go the route where the red compound is our electrophile. So how would we begin? We're going to begin with isobutyl alcohol. In the first step, we're going to treat it with sodium hydride. And in the second step, we're going to treat it with the primary alkyl halide. And if you wanted to choose a bromide instead, that's fine. I'm going to stick with the iodide just because, okay? And then that's going to give you the desired product. Give me a thumbs up if you follow me on that one and why you can't use this, why you can't use the isopropyl iodide. All right, if you're not following me 100% of the way, watch carefully. If you were to start with this as your alcohol, right, this, OH, and then you deprotonated it using sodium hydride, you'd end up with this as your alkoxide, okay? So far, so good. But then if you try to react that with isopropyl iodide, this is a secondary alkyl halide, right? This goes back to chapter 7. If you don't believe me, look at chapter 7. This is figure 7.20, I think it is in your book. I don't remember exactly, but figure 7.20, there's a whole table about this. And what you would get here is you would actually get mostly elimination. So you'd mostly end up getting this, okay? And you'd regenerate the alcohol. So it's not very useful. Again, does everybody follow me on this? Just want to be sure before I move on to the next one. All right. All right, good. There we go. I don't know why I couldn't see what you had written there for a second, but it seems like I'm back in action now. Okay. There we go. Let's take a look at the next one. Take a look at the next one. Let me just delete this. Okay. The next one. I don't know why they had to draw it as this condensed methyl group. It's kind of annoying. But if I redraw the compound like this, I have a methyl group up here. I've got an oxygen, and then I have another methyl group. I could either break it here so that my electrophile would be iodomethane, CH3I, right? I need this CH3 group. Or I could break it over here so that my alkyl halide would be this. Well, hopefully you can see that the one in red is the best option because it is methyl, right? It's a methyl halide. So methyl iodide is what this is called. And this is just a tertiary alkyl halide. So that's only going to give you elimination. And so our synthesis would look something like this. We'd start with the tertiary alcohol, like this. In the first step, we treat it with our base, sodium hydride. And then in the second step, we would treat it with methyl iodide. And then we'd end up with our product like that. So again, this is just a gentle reminder. I guarantee you that I'm going to ask you a question like this on the quiz. Or I'm going to say, which one of these is the viable way to produce this ether? And you have to know, if there's two possible routes, you have to know which one is the best one. So when you're looking at a Williamson ether synthesis, you always have to remember that the Williamson ether synthesis, which is what's covered on this slide, is only going to work well with what? Primary and methyl alkyl halides. We could even jot in here, will not work with secondary or tertiary, right? If you treat it with an alkoxide, a secondary alcohol is going to give you mostly E2 and a little tiny bit of SN2, whereas a tertiary is going to give you only E2, okay? And again, if you go back to that figure 7.20, you could look at the information there. All right. Where was I? I was over here. So identify the reagents that you would use to prepare each of these using what? Alkoxy. So it's not oxymercuration demercuration, it's alkoxymercuration demercuration. In the first step, we're going to use mercuric acetate and our alcoholic solvent. And then in the second step, we're going to use sodium borohydride. Right? In all of these questions, or in both of these questions, this part and this part and this part doesn't change. The only thing that you need to identify is what's the R group going to be for your alcohol. Well, with this alkene, if I'm adding an ethyl group and an oxygen, my alcohol will be ethanol. So my reaction steps would be, I don't know why I keep skipping around like that. Skip around the room. Come on. There we go. The first step would be mercuric acetate, ethanol, and the second step would just be sodium borohydride. All right, could anybody name what the alcohol would be? And the second one, we did nomenclature of alcohols last chapter. Could anybody name that? Yeah, cyclobutanol. Absolutely. Yes, right? And the first one we had ethanol, and here we have cyclobutanol. So first step is going to be mercuric acetate, cyclobutanol, which is this, a cyclobutane with the hydroxyl on it. And then in the second step, we use sodium borohydride, just like that. Alkoxymercuration, demercuration.